All right, time for some new content. We're jumping into bitwise operations now. So this is building off everything that we saw with integer representation. So quick revision on the content that you saw literally 5 minutes ago. Remember, all data on a computer is represented in base 2 or binary, and each of these digits, each of these binary digits we call a bit, can either have a 0 or a 1 value, and computers tend to group these bytes into sets of 8 bits. Okay, now the other important thing to remember is that information on a computer depends on two things. Number one, the data, the actual bits that we're storing, as well as the context that we use it in. So let's say, for example, I take this value, these 8 bits, and we're going to look at these 8 bits as if they're an unsigned numeric value, in which case it would represent the number 73. And if we were to look at it as a character, if we were to match it against the ASCII table, we would say that's a capital I. What if we had a group of 4 bytes? In fact, let's pull up MIPC. I know that we're officially mostly done with MIPS, but let's pull up MIPC anyways. And let's set up a data segment. Inside this data segment, I'm going to enter in some integers. Actually, I'll enter in a single integer. Let's call it value. And I'm going to give it the value 424445. Okay, so this is some numeric value in hexadecimal. We could use system call number 1 to print out this value as an integer. So I'm going to write up a main function. And inside my main function, I'm going to use syscall number 1. So liv01. Lucas, I hope you've already finished the assignment. Otherwise, you might be in a bit of trouble there. Otherwise, let's load this value from memory using the load word instruction. We want to load it into A0 since we know that's where syscall is going to look. And we will load value, syscall jr $array. And hopefully what we see, if I run this, is we get this numeric value being printed out. So this value is really just the same as this value, except that's being printed out in base 10 because this particular system call in MIPC prints out integers in decimal. So this system call has been designed to print out integers in decimal. So it's going to look at the individual bits behind that value and print it out in decimal. But we have a group of 4 bytes, right? This value is a word. It occupies 4 bytes. What's stopping me from taking those 4 bytes and instead of treating it like an array of, instead of treating it like an integer, I treat it like an array of 4 characters instead. So what I could do is I could quickly write up a loop. Should I bother with good style? I'm going to bother with good style. I'm going to set an example. Main loop init. We'll just start our loop counter at 0. What else do we need? We need a condition. In the condition, we'll loop until I gets to 4. Whoops, that's not right. So BGE up until I gets to 4. We will go to the loop end. And now in the body for this loop, I can't stay consistent with style apparently. In the body for this loop, what we're going to do is instead of loading this value as a word, I'm going to load each individual byte from that value. So let's go main loop body. We can use a load word instruction. And instead of loading values as, instead of using system call number 1 to print these values out as numeric decimals, I'm going to use the system call number 11. What does system call number 11 do? It looks at the value of the byte, and it checks that byte against the ASCII table, which we can always pull up using man7 ASCII. It checks the value of that byte against the ASCII table in order to determine what character representation it should print out. So going back here, we will use system call number 11 to print this value out as a character. I'm going to load a byte, whoops, that's not load byte, load a byte from memory. into A0. And where is this byte going to live? It's going to be this base address plus I. I want to iterate over each of those 4 bytes. So I can take the base address of the array, which is a value, plus I. And then we can use syscall. So what I'm going to do is I'm going to iterate over each of these 4 bytes. And what we should see, if we run this, is that I'm missing an end label. There we go. Let's try that again. That's not good. We only have the first character because right now my loop isn't actually looping. Bit of a rookie mistake. So let's just make sure we add that. We want to increment I, so we'll say, whoops, add I, t0 is equal to t0 plus 1, jump to main loop body. OK. Condition. This is going great. Hopefully that's better. Maybe. What have I done wrong? See, this is why you need to be consistent. Cool. There we go. So we get each of those characters being printed out on their own. And why does this happen? Because we have a group of 4 bytes being stored in memory. That's what .word is doing. It's initializing a group of 4 bytes in memory. And those 4 bytes collectively represent some numeric value. But we could choose to interpret those bytes as an array of 4 characters instead and print those out as characters. So in hexadecimal, the value was 0x42434445. We can see that these bytes are being stored here. Question, why are these bytes in reverse? Who actually watched last Monday's lecture? Why are these bytes being stored in reverse in memory? Yes? Yes, that's because MIPS CPUs and most modern CPUs are little endian, so they essentially reverse the order of bytes when storing them. OK. Yes, so if we were to look at this numeric value, we would get the number that printed out earlier. If we were to look at them as characters and match them against the ASCII table, I can see that 42 over here, 0x42. In hexadecimal, let's look at hex 42. Hex 42 is capital B, which is why we get B being printed out. Now, one thing to note is that if I were to run this on a big endian system, which don't really exist these days, if I were to run this on a big endian system, since the bytes would be stored in their regular order, we would get B, C, D, E being printed out there. OK, so that's just a quick reminder on how integers are represented. Now, let's talk about bitwise operations. So we have some operations in C, which COMP1521 did not tell you about. So bitwise operations provide us with a way to manipulate the individual bits of a value. So we know that everything behind the scenes is being represented just as bits. We can manipulate those bits using these 6 bitwise operations. So you might notice that some of these symbols might seem kind of familiar. If we look at the ampersand symbol, you've seen the ampersand symbol being used for if statements. That ampersand symbol, typically inside if statements, has 2 ampersands next to each other, and that's separate to this, where we've only got 1 ampersand. So 2 ampersands is what we call the logical OR operator. It's what we use to check if 2 conditions are true simultaneously. This ampersand operator is the bitwise AND operator. So 2 separate operators, you don't want to get them mixed up. You always want to make sure that you've got 2 ampersands when you're checking if 2 conditions are true. Bitwise AND, we will see its applications very, very soon. Same sort of deal with bitwise OR. And then we have a couple of operators which are kind of new. I mean, the left shift uses the less than operator. I mean, it uses the same symbol as the less than operator, but it is different. OK, so the first kind of bitwise operator we're going to look at is the bitwise AND operator. So what it does is it takes 2 values. For example, I could have a value stored in the variable A and a value stored in the variable B. And what it's going to do is it's going to perform a logical AND between each pair of corresponding bits. So if I were to enter in 2 values, actually, someone give me a random value in decimal that's smaller than 256. 7. OK. So what's 7 in binary? Well, I know that 7's really just 4 plus 2 plus 1. So that's going to be 1, 1, 1. And as my other value, I'm going to choose the number 5. So the number 5 we can really just say is 4 plus 1. OK, so these are our two values. Our first value is the number 7 in decimal, which is really just represented as that behind the scenes. And our second value is the number 5 in decimal. OK, and how does the bitwise AND operator work? Well, we take each column. So we take pairs of corresponding bits by taking each column from the right. And we look at these two values. I'm going to put an ampersand here to clarify that we're using bitwise AND. We look at each of these two values. If they're both 1, if they're both set to a 1, then we place a 1 in the resulting bit, in the resulting column. Over here, we can see that there's only 1 bit set. So in that case, it's just a 0. Over here, we can see that both bits are set. So we get a 1. And over here, no bits are set, so all of these bits will remain as 0. So that's how the bitwise AND operator works. You essentially just take each of the bits in a given column. You apply the same kind of logic as the logical AND operator that we've seen before for that particular column, and we produce a result. So from ANDing the numbers 7 and 5 together, what result do we get? Well, we can see that the result is really just 4 plus 1, which is just 5. So the result of ANDing 7 and 5 is really just 5. Let's make this a little bit more interesting. Let me throw some random 1 bits around. OK, what happens if I AND these two values together? Well, now we can see that this column stays unaffected because there's only a single bit set. But this column, we have 2 bits set, so I'm going to place a 1 there. So the result of ANDing the values 32 plus 4 plus 2 plus 1, that's 39. So that's 39. That is 32 plus 16, 48, plus 5 is 53. We can see that the results of ANDing 39 and 53 is, that is 37. Cool. And you could always quickly verify this with a C program. Bitwise operators are C operators, so I could quickly write up a quick program. And.c include standard IO. Oops. And we'll just use printf %d and print out, oh, spoilers. We don't like spoilers here. All right, let's do 39 and 53, and let's see what that value is in decimal. Yeah, I can type. There we go, 37. So that's what's happening behind the scenes with our bitwise operations. And once again, the main thing I want you to remember, the only reason the result here is being printed out in base 10, the only reason our program spits out a decimal output is because if we go back to the program, if we go back to this program, let's do that again, we can see that we're using %d here. We can see that we're using %d. %d means decimal. So there's code inside printf, which is looking at the individual bits of our value and doing some magic to convert that to something in base 10. All right, so that's our first operator. Now let's look at our next operator. Our next operator is, actually no, let's do something more interesting. All right, so in COMP1521, when you've wanted to check if a integer value is odd, you'd write some code like this. Take the value, divide it by 2, see what its remainder is. If there's a remainder of 1, then we know it's odd. So that's how they want you to do it in 1511. But in 1521, there's a little trick that we can pull. So let's take the values 6 and 7. 6 and 7, and let's represent them in binary. So I'm just going to get rid of this, get rid of all of this, and I'm just going to have the value 6 and 7. So 6 is 4 plus 2. And 7 is that. OK, so 6 is even, 7 is odd. In order for a value to be odd, we know that there has to be a bit set in that column, right? Because that's the ones column. Also, people at the back, can you see that, or should I zoom in? I will zoom in anyways. There we go. We can see that our ones column has a 1-bit set if the value is even. Because if we look at all of these powers, the only power which is odd is this one. So in order for a value to be even, then we know there has to be a 1-bit set. So what I'm going to do is I'm going to take this value, take our 7, keep it up here. And what I can do is I can actually use bitwise operations to check whether a particular column, whether a particular bit of a value is set. So what I could do is I could place a bunch of whoops, that's not what I want. Let's just copy paste this. Cool. I could take this column, and then in my second value, in the second new arbitrary value that I've just constructed, I'm going to place a 1 in that position. And what's going to happen is if I have an odd value and I AND these two values together, if I take an odd value and AND these two values together, what do I get? Well, this is going to give me a 0, that's going to give me a 0, but that's going to give me a 1. So that's going to give me a 1, and all of those bits give me zeros. So I can see that if I have an odd value and I want to check if this particular column is set, what I can do is I can AND it with this special constructed value which I've created in order to check whether the bit in that position is set. Because let's say that I change this to be the number 6 in decimal instead. The number 6 is even, so we have a 0 in that position. What happens when I AND these two values together? Well, that's going to give me a 0. All the other columns are going to give me zeros. So it turns out that when I'm checking whether a particular position is set, whether a particular column is set, in this case, this one, and it turns out that the particular column is not set, I get a 0 as a result of ANDing with this arbitrary constructed value. Oops, this arbitrary constructed value. So what is this arbitrary constructed value? So it's a value that I've created to check whether a particular column in my original value is set. And we have a special term for this arbitrary constructed value. It's what we call a bit mask. So this is a special bit mask. This is what we call the bit mask. And the bit mask essentially allows us to, it's essentially a value that we've constructed for some purpose. In this case, I've constructed this mask in order to check if a value is odd or even by checking the last column. OK, so this bit mask, this is a binary value. What happens if I convert this binary value to decimal? What value is this really in decimal? It's just the number 1, right? So in order to check if a value is even, what I can do is I can take that value. Oh, I've already got slides for this. Very nice. I can take that value, n, and AND it with a number 1. So if the value is odd, it's going to give me a 1 as a result. If the value is even, it's going to give me, oh, that slide is broken. That should be a 0 in that position. Pretend there's a 0 here, but other than that, if the value is odd, it's going to give me a 1. If the value is even, that should give me a 0. OK, so at this point you might be asking yourself, well, clearly this is this is like shorter code. There's less steps involved. Does that mean that when I'm writing an is-odd function, I should do this? And the answer is no, because generally speaking, when you write code, you want code to be readable. You want it to be super obvious. And to some people, that might not seem very obvious as to what it's doing. And the good news is that most modern compilers will automatically optimize something like this to use bitwise operations instead. So most modern compilers are really smart when it comes to dealing with powers of 2, and they will substitute in bitwise operations for you. However, in this course, when we give you lab exercises, we expect you to do those lab exercises using the bitwise operations that we specify. So real code, don't do this. In this course, please practice your bitwise operations. OK, so that's bitwise AND. Also, there's a lot of code on GitHub which purports to check if numbers are even for you. Most of those pieces of code are just massive if-else statements. Don't actually use them. OK, bitwise OR. So we've talked about bitwise AND. Oh, actually, one more thing. going back to this function, we can see that it can return one of two values. It could either return the number 1 or the number 0. And that works out for us because we know that in C, any non-zero value is considered to be true. So in this case, the isOdd function will return 1, which is a truthy value if the value is odd, or it will return 0, which is considered false by C. It will return the value 0, which is considered false by C, which is why this notation works. So we don't have to do something like return n and 1 is equal to 1, because the number 1 is already considered truthy. OK, bitwise OR, same kind of deal. We look at each column one by one. So let's go back in time a little to when we had, this is going to take some time. Let's go back in time to when we had these two values. And now, instead of using the AND operator, I'm now going to use the OR operator. So what the OR operator does is it looks at each column individually once again, except this time, we only want to check if at least one of the bits has been set. So if the column contains 2 zeros, then we get a 0 as a result. But as long as at least one of these 2 bits have been set, then we get a 1 as a result. So here we can see that at least one of the bits has been set, so we get a 1 in the result. Here we can see that at least a single bit has been set, so we get a 1 in the result. Same sort of deal over here. In this column, we can see that there are no 1s, so we get a 0 as a result. 0 as a result. Here, that's a 1. Here we can see there's a 1. Here there are clearly no 1s, so they get 0s as results. And that's your bitwise OR. That's how we can OR values together. Now, where might we want to use this? Why is this actually useful to us? Well, let's talk about that a bit later. But essentially, bitwise ORs are pretty useful if you have a value and you need to change one of the bits or some of the bits of that value. And we will see a demo of that relatively soon. But before I do that, there is one more operator that I want to talk about, actually 2 more operators that I want to talk about now. Bitwise XOR. Bitwise XOR is kind of like the bitwise OR, where we checked if at least one of the bits was set. Except with the XOR, we need exactly 1 bit to be set. So it takes 2 values, and it sets the resulting bit in a column if exactly one of the original bits in that column was set to a 1. So let's take a look at this value. Let's reset it to use an XOR instead. One thing that you might notice is that the XOR symbol is the caret over here, the caret operator. It's like the little hat sort of thing. In a lot of languages, the hat symbol might be used for powers. In C, the hat symbol is used for the bitwise XOR. So if you want to use powers in C, you can't use this. You have to use the power function in the math library. OK, so I've got 2 values. That's not 6, that's not 7. That's not a caret, that's a C-A-R-E-T. OK, so let's take a look at this column. So for the XOR, I want exactly 1 bit to be set. I want exactly 1 bit to be set. Here we can see that we've got 2 bits set, so that produces a 0. Over here, I can see that exactly 1 bit is set, so I get a 1 there. Here, it's not exactly 1, it's 2, so that's a 0. That's a 0. Here we have exactly 1, so that's a 1. That's a 0, 0, 0. And that's your XOR. All right. So XOR is really useful for cryptography, which we don't talk as much about in this course. But it's also really useful if you have a bit that you need to flip. So let's say let's say my original value has a 0 in a position, and I want to force it to flip to a 1. Or let's say my original value has a 1 in a position, and I want to force it to flip to a 0. I can use this to kind of switch bits. And we will see demonstrations of this eventually. Actually, let's see a demonstration of it right now. OK. So let's just go to here. Actually, I should already have this open. There we go. I'm prepared. So essentially, this is a very, very bad way to sort of try to encrypt a value. So what I'm going to do is I'm going to define an XOR value. Let's say I choose to XOR every value in my string with the number 42. So what it's going to do is it's going to read a character. It's going to XOR it with the number I specified. And then it's going to print it out. So let's take this program, gcc xor.c-o XOR. Now the XOR expects a command line argument, which is the key that I want to XOR each of these values with. So I'm going to XOR each value that I enter, each character that I enter, with the number 42. Hello world. And I can see that it prints out this string. Now what's really cool with the XOR function is that it's kind of reversible. So when you XOR a value with another value, so let's say I XOR each character with this, it produces a result. So this is kind of my encrypted result. And what I can do is I can reuse XOR to decrypt this value. So I run this program again with 42, and I give it this input. And what it's going to do, oh, actually, I already did it. Let's do that again. I'm going to use 43 as my key instead. Hello, world. Oh, it's still got a new line. That's annoying. But I'll take that. I will run it through my program again. Whoops, that's the wrong value, 43. Paste that. And what it's going to do is it's going to decrypt my string. So the XOR value, sorry, the XOR operation is what we call a symmetrical operation. So when you XOR a value, that's kind of how you encrypt it, but it's also the same thing that you use to decrypt it because it's a symmetrical operation. It goes both ways. So that's a very, very sort of basic encryption that we can perform with XOR. Okay, so real encryption algorithms actually kind of build upon this concept, but real encryption algorithms are not symmetric because that's, I mean, a lot of real encryption algorithms are not symmetric because that might be bad. So if you want to know more about how encryption algorithms work, Richard Buckland has a course on that, which you can take next term. Let's move on to our next demonstration. Our next demonstration is doing this in MIPS because we're not fully done with MIPS. This is the last bit of content that we need to talk about in MIPS, and that is how to use all of these bit manipulation operations with MIPS instructions. So these are relatively self-explanatory. They're like all the other arithmetic instructions that you've seen, except now these arithmetic instructions can do bitwise operations as, now these instructions also allow you to do bitwise operations as well. So going back to that program we saw earlier, which was capable of checking whether a number was odd or even, we can go ahead, we can implement that in MIPS. So here is my C program. I want to modify the C program so that it's not using the modulo operator. Instead, it's using the ampersand operator, the bitwise AND operator. So what I can do is I can AND it with the number 1 to check if it's odd or even. Now that I've got this, I can try to translate this to MIPS. So let's open this up. I've done most of the hard work in MIPS already because you're probably sick of seeing me type out MIPS code in lectures. So the only thing that we need to do here is implement a branch instruction somewhere. We need to implement a branch instruction over here to check if the value that we read in, is that Copilot? No, that's not Copilot. We need to check if the value that we read in is odd or even. So what I can do is I can use the bitwise AND operator, take that value, AND it with 1 to check if it's odd or even. So the value I read in is inside T0. I'm going to take that value. I'm going to AND it with 1. So T0 ANDed with 1. And then I need to specify a destination. I'm going to use T1 as my destination. There we go. And T0, T1. So what this is going to do is it's going to take the value that we've read in, AND it with 1, and then it's going to give us a result. If the result is 0, then we know that the value is even. If the result is 1, then we know that the value is odd. So this is if n ANDed with 1, then we need a b and ez to check if the value is non-zero. So if the value is, actually no, if the value is 0, I want to go to that label. So if b equals z, we'll take t1, check if that's 0, and go to main is even. There we go. Otherwise, it's going to print out this message saying that the value is odd. So let's go ahead, run that in MIPSy to make sure it works okay. 1521 MIPS, no, MIPSy odd even.s. Enter number. 4 is even. 5 is odd, and all we're doing here is we're checking the last bit of that value that we enter in and checking if that bit is set. Okay, so that's how we use bitwise operations in MIPC, and hopefully that is the last piece of MIPS code that we need to write in lectures. Moving on. There are 2 more operations that we need to talk about, 3 more operations that we need to talk about. I think I'm missing a slide somewhere. We are missing a slide. Okay, there is 3 more operations that we need to talk about. The next one I'm going to talk about is the simplest. So the next operation only takes in a single value, so let's get rid of this. Takes in a single value. And what it does is it looks at each individual bit and it then flips the bit. So this is the bitwise not operator. It takes a value and then it flips the bit. So the 1 turns into a 0 here, the 0 turns into a 1, 1, 0, 0, 1, 1. Dead simple, that's all a bitwise not is. We will see some uses for the bitwise not very, very soon. Okay, now left shift. So what the left shift does is it takes some value and then it pushes it over to the left. So it takes a value and a small positive integer x. So what I'm going to do is I'm going to enter in some value. Someone suggest a value. 7. Someone really likes the number 7. I also really like the number 7. Okay. There's our number 7. Now, before I do this, I want to think about base 10 instead. So let's say I have some base 10 place values. So let's say I have a thousands place, I have a hundreds place, I have a tens place, and I have a ones place. And I take the number 70, and I decide to take the digits of that. Actually, let me just draw a line here so we know what's a place value and what's an actual digit. So I take the number 70, which is really just this. Leading zeros don't make a difference. And then I decide to take this value and then shift them to the left, so that instead of the 7 being in the tens place value, it moves over to the hundreds place value. So the 70 is going to be shifted over here. This 0 is still going to be there. But now we have an extra spot on the right. Whenever we have an extra spot on the right, we're just going to fill it with a 0. So by taking a value in base 10 and shifting it to the left by 1 position, what mathematical operation have I effectively done? I've multiplied by 10. So in base 10, when I shift a value to the left, I'm really just multiplying by 10. Now, if I'm working in base 2, if I just have a 16s, a 8, a 4s, a 2s, and a 1s, I'm working in base 2, and I have the number 7, and I decide to shift it to the left. Does anyone want to guess what mathematical operation that does? What was that? Times 2. So yeah, in base 10, when we shift to the left, it multiplies by 10. And base 2, when we shift to the left, it multiplies by 2, with some catches. So yes, shifting to the left, essentially when I have a value and I say I want to shift it to the left by 1, I take that value, I drag it over to the left by 1 position. Actually, I need some extra place values. Let's bring all of those in. Okay, so I take it to the left. Let's also just remove all of this for now. And I shift it over 1 position to the left. Cool. And any spaces which appear on the right just get filled with zeros. So there we go. I can see that when I take the number 7 and I shift it to the left by 1 position, I get 8 plus 4 plus 2, which is 14. So shifting to the left usually multiplies a value by 2. But there are some catches. Let's say that instead of having the number 7, I decide to have the number 135. So the number 135 looks like this in binary, right? That's the number 135, 128 plus 4 plus 2 plus 1. Now, for the sake of this example, I'm working with 8-bit integers. So these are U and 8Ts for the sake of this example. Now, what's going to happen when I drag this over to the left? We get a 0 in this position on the very right. But with my UN8T, I can see that I don't have room for this bit on the left anymore. This bit fell off. This bit fell off the end. So what happens is this bit now disappears. We now lose that bit of data. So it turns out that when we take the value 135 and we shift it left by 1 in a 8-bit system, we lose that bit on the left. So 135 times by 2 in an 8-bit system is really just the number 14, apparently. So you have to be careful when you left shift to make sure that you don't essentially fall off the bounds of your integer type, because then you might lose data. So that's just something that you need to consider when left shifting. OK, and we can left shift by bigger values too. So instead of shifting by 1, I could shift by 3. All I do is I take this, and I drag this value over to the left by 1, 2, 3 places. These 3 bits fall off, and any new spaces to the right are filled with zeros. There we go. All right, so left bit shifting, hopefully relatively straightforward for everyone. So since we have left bit shifts, you can probably also guess that we also have right bit shifts. So let's undo all of that, go back in time a little. There we go. Let's do some right bit shifting. OK, so right bit shifting, sort of the same deal. So you take a value, and you take a small positive integer, and you can essentially drag that value over to the right. So any bits that fall off the right are going to vanish, just like bits on the left vanish for left shifting. New 0 bits are inserted on the left with some catches. And the result always contains the same number of bits as the input, as we saw with the previous example as well. So going back to base 10, if I had the value, let's say 110, 1, if I had the value 570, and I decided to shift it to the right, what mathematical operation is that equivalent to? What was that? I'm hearing a lot of divide by 10s. That's good. So you won't believe what happens if we do the same thing in base 2. If I do the same thing in base 2, 1, 1, 0, and I drag it over to the right by 1 position, then I get 1, 1 over there. That 0 falls off. And I get, well, this value is 6. This value is 3. We are essentially just dividing by 2. OK. So let's do another worked example. Let's take this value. Let's remove that there. OK, let's take the number 7, since it's apparently really popular. Now I'm going to take this value, and I'm going to shift it to the right by 1 position. What's going to happen? I drag it over to the right. Now this one's really wide, but it's fallen off the end, so that one's now disappeared. And any new bits that appear on the left get filled with zeros, like that. So what happens here? Well, our original value was 7. Our new value is 3. Now you might be thinking 7 divided by 2 is not 3, it's 3.5. But you've got to remember we're constrained to integers here, and when you do integer division in C truncates. So this is behaving as expected. OK. So that's right shifting. Now, right shifting only really behaves as expected if you work with unsigned integers. So typically speaking, you should never right shift a signed integer. You should never right shift a signed integer, because that's undefined behavior. Different computers can do different things for unsigned representations. For signed representations. So yeah, shifts involving negative values may not be portable and can vary across different implementations. So it really depends on the CPU often, depends on the compiler. It's a common source of bugs in COMP1521, and in fact, DCC will explicitly warn you and prevent you from right-shifting signed values. So always use unsigned values and variables when right-shifting to be safe and portable. If you're interested as to why we don't want you right-shifting signed values, especially signed negative values, post to the course forum, and I'm sure Xavier or I will write up a nice essay as to why that can be problematic. And in fact, does this talk about it? Here we go. Yeah, so here we have int16t. Int16 is a signed type. It doesn't start with a u, so it's a signed type. So if I take the number -1 and I right-shift a negative value, that's considered undefined in C. If I take it, if I take a negative value and I left-shift it, that can also cause me problems. So that's also considered undefined in C. So negative values, you generally should not be shifting at all. You should be using unsigned types when you shift. If we look at this value, we have 32767. So let me think about how 32767 is represented in a 16-bit signed system. So in a signed system, the leftmost column is multiplied by -1. So that's how 2's complement works. The leftmost column is multiplied by -1. Holy shift indeed. OK, so let me think about the number 32767. 32767 is essentially all of these columns just added together. If you don't believe me, you can pull up a calculator, but that's just 2 to the power of 15 minus 1. 32767, which is how I get this. OK, so that's 32767. What happens if I take this value and I shift it by one place to the left? So I grab this value and I shift it to the left by one place. So that turns into a 1, that turns into a 0. Oops, that turns into a 0. And all of a sudden, the representation of this value isn't a multiplication by 2, right? Because this column is not 2 times the previous column, it's a negative column. So what we've just done is we've created a negative value by left-shifting a positive number. And that's kind of bad because it doesn't do what we expect in terms of multiplying by 2. So that's what we consider to be undefined behavior in C. Different CPUs might deal with that differently. So we don't want you doing that. And again, we will talk about that on the course forum if you ask us. Even this is a problem. So even if we look over here, we're using an uint64t. So that seems pretty safe, right? We're taking a uint64t, which is taking the integer 1, and we're left shifting it by 33. But in C, when you type in an integer in your code, that's what we call an integer literal. And integer literals are assumed to be 32 bits. So when we have an integer literal, it's trying to perform bitwise operations on them in a 32-bit space. So if you have a 32-bit space and you try to left shift it by 33, that's going to cause you problems. It's going to cause a value to fall off, which is considered undefined. So instead, what you need to do in order to force your bitwise operations to occur in a 64-bit space is take the number 1 and cast it to use 64 bits instead. So integer literals are assumed to be the same size as an integer, which is usually 32 bits. That's going to cause a problem, so instead we force it to be a uint64t. This also works. 1LU takes the number 1, and it converts it to a long unsigned value, which should be 64 bits. Now, once again, there are MIPS instructions for doing the same thing. So we have a bunch of left shift and right shift values. So there's SRL and SRLV. So SRL shifts values to the right. But when it shifts to the right, it fills the leftmost places with zeros. Whereas if you take SRA, SRA shifts to the right, but it fills the leftmost value with a copy of the most significant bit. And the reason for this distinction and the reason for the entire undefined behavior that we discussed earlier, you can ask about on the forum, and we will type something out. But generally speaking, the reasons for it aren't too crucial for understanding this course. OK, so what you can do is you can write up a quick C program in order to perform some bitwise operations on some values. But what I want to point out, over here is a function that we've written. So in C, we have %d to print out decimal values. We have %x to print out hexadecimal values. But what C doesn't have is a %b to print out values in binary. So remember, at the end of the day, everything behind the scenes is really just binary. It's up to printf to decide how it displays values to us, right? So printf is kind of like that interface between what's in the computer and what we see in the outside world. In fact, printf is just using a syscall behind the scenes, which we'll talk more about in week 7 or week 8. So printf decides how we see values, and printf doesn't have a way to print out values in binary until next year, right, Xavier? Is that being added next year? Yeah. So next year there will be. What's that? Okay, assuming things go to plan, C will add a feature which allows you to directly print out binary values. But unfortunately, it's not next year yet, so we don't have that option. Instead, we have to write our own sort of code to look at the individual bits of a value and print out a 0 or print out a 1, depending on whether that bit is set. So how does this program work? Let's say that we have a 64-bit value, and we want to see if a bit in a particular position is set. So we have a function which extracts the nth bit of a value. So for example, let's say I have, let's go back in time a little, back to 8-bit land, and let's keep going back until I have 2 values. That's a lot of undoing. There we go. So here I have a value at the top, and my goal is to essentially check if each bit in a particular column is set. So what I can do is I can construct a mask which has a 1 in this position and have all of these bits be zeros. And what this is going to let me do is check if a bit in a particular column is set. Because if I AND these 2 values together, we know that ANDing them together will give me a 1 if that bit is set, or a 0 if that bit is not set. So what I could potentially do here, is let's say I want to check if the rightmost bit is set, so the first bit from the right. What I can do is I can just AND these 2 values together, and that will tell me that this particular bit is set. But let's say I want to check if the 4th bit from the right is set. So I want to check if this particular bit is set to a 0 or set to a 1. What I could do is I could take this value and shift it to the right. Shift it to the right like this. Whoops. 1, 2, 3, 4. So all those bits are going to fall off the end. So I've shifted it to the right by 3 places so that the bit that we care about is now aligned with this one in the mask. And what this allows me to do is check if the bit in that column is set. Because if I AND these 2 values together, that's going to produce a 0, which tells me that this bit in the original value is not set. So that's what the code over here is doing. It takes the value and it shifts it over to the right so that the bit that we want to check is in the rightmost column, so that it's in the column of the least significant bit. And then once we've shifted that value over so that the bit that we care about is on the very right, we AND it with the 1. And when we AND it with a 1, we check if the particular bit in that column is set. If it's not set, we get a 0.
Could you AND it with 1 bit shifted to the right?
So that's the other solution. That's the other solution. So instead of shifting my original value around, how much time do I have? I have a minute. What I can do is I can change my mask to check this particular column instead by taking the number 1 and left shifting it by 1, 2, 3, 4. Oops, let me just add some more columns here. What I can do is I can take this mask and I can left shift it by 1, 2, 3. There we go. So this is all going to get filled with zeros. And what happens when I AND these two values together? Well, when I AND these two values together, we don't need this anymore. When I AND these two values together, I can see that this is all going to give me zeros. And if I look at this column is also